Like I said, our last keynote is going to be from Professor Prorok. Amanda is a professor of collective intelligence and robotics in the Department of Computer Science and Technology at Cambridge University and a Fellow of Pembroke College. Her lab's research focuses on multi-agent and multi-robot systems. The mission is to find new ways of coordinating artificially intelligent agents to achieve common goals in shared physical and virtual spaces. Pioneering methods for differential communication between learning agents, using methods from machine learning, planning, and control, etc., with numerous applications. Prior to Cambridge, Amanda is a postdoc at Graph Lab at Penn, and she completed her PhD at EPFL, Switzerland, where she won the prize for the best computer science thesis at EPFL. She's also received numerous early career awards, competitive grant programs, and best paper awards in international conferences. Thanks so much, Amanda, for joining us. Now let me just see your slides up. I think you'll pop up once you start talking. So take it away.
Yep. Test. Do I pop up?
Perfect. Thank you.
Fantastic. Great. Thank you so much, Jake, for organizing this workshop together with your colleagues. It's so timely, and I'm really glad that you were able to put this together and bring this through. Yeah, and it's a delight to be participating in this really great schedule. Let me just begin the talk by saying that I live in Cambridge for over 7 years now, and I'm still trying to learn how to drive on the wrong side of the road, perhaps as a testament to how difficult the symmetry problem actually is, even for humans. Right, so today I'm going to be talking about leveraging symmetry for learning robot interaction models, and I'm going to be deep diving into one particular research thrust that we've been working on for the last 3 years. Before that, I'm going to intro a little bit of what we actually do at my lab, since I appreciate we've not really talked about any multi-robot system work in today's workshop. So what is it that we do at my lab? So the mission of, or the vision of my lab is that the next wave of computing is about agents that communicate and coordinate. And what I hope with this talk is that I will be able to excite you about the kinds of things that we can do due to the confluence of AI communications and mobile computing, and how we're actually specifically looking into different various methods that help us in this process of devising policies for such multi-robot systems. Why are we so excited about multi-robot systems? Well, I'm going to contextualize this a little bit for you. So here you can see a couple of movies and GIFs showing you the kinds of things that we will be able to do in the near future, or are already doing today, as in the case of agriculture and indoor warehouse logistics. And why this is so important for today is because I think that these kinds of applications are really going to be helping us tackle the challenges of urbanization and dense living, and also environmental change, all of which are really pressuring our planet to deliver more resources more quickly. And so we're really looking to multi-robot systems that are able to distribute over scale and time in order to help solve these kinds of problems. So why is this an interesting research program? Well, it turns out that we can organize solutions to these kinds of multi-robot problems roughly along these two axes that I'm showing you in this cartoon here. So what we see on the vertical axis is the increased ability to deal with partial information problems. In other words, we're looking at how much an individual robot knows about the full problem at hand. And on the horizontal axis, we're looking at increasing scale and complexity of the problem, so higher degrees of freedom or even heterogeneous agents performing parts of the problem solving. So what we have today is solutions that work really well for problems that are either fully observable or relatively small in scale, or work for relatively small degrees of freedom. But what we're really missing, or we have a lack of solutions for problems that I'm kind of terming online scalable here, which are problems where the configuration space is typically high dimensional, where frequent replanning might be needed, where we want to satisfy global objectives, but we ideally want to rely on only decentralized information dissemination schemes. And so using first principles approaches or solvers, or even hand design solutions to problems in this orange regime here is actually quite difficult. And this is really the regime where we think that data-driven solutions make a lot of sense. And so in my work, we really focus on both end-to-end learning paradigms as well as hybrid mechanisms to help us solve these online scalable problems. So today I'm going to be focusing on one specific instance of of an online scalable problem. And I'm going to be addressing a couple of the challenges that come as a result of trying to tackle these problems. So typically, the first challenge we encounter when trying to devise solutions for these problems, when we're looking at synthesizing policy, is the choice of training paradigm. And this can be either reinforcement learning or imitation learning or supervised learning or the variants thereof. The other challenge that we have, irrespective and independent of the learning paradigm, is that we're often faced with high-dimensional joint action and observation spaces. We already have these challenges in single-agent systems, and they're only exacerbated in multi-agent systems, where we're looking at combinations of each individual agent's observation and action space. And finally, compounding all of this is that we still want to be sample efficient, we still have a sim to real gap, and we still want to be able to generalize to unseen instances as we deploy our systems in the real world. So how are we going to tackle this? Well, there are various methods that we're pursuing in my lab, and today I'll talk a little bit about how we looked at one specific problem where we thought that leveraging symmetries would make a lot of sense to reduce the dimensionality of the problem as well as boost the learning itself. So before that, I'm going to give you a quick high-level overview of how we even go about modeling this idea of robot interaction through functions that approximate what robots perceive or how they input information coming from other robots in the system. So we basically begin with this model phi O of j, which can be taking in an observation coming from a robot that I'm terming robot j here. And it's going to output some information that is going to, in some way or another, influence the decision-making process of another robot I here. So it's going to influence its decision or action I. And phi of OJ, or phi of contextual information coming in from robot J here, is going to be a function that's going to approximate this interaction. And what's nice about the model, or the way that we're going to design this model, is that we're going to we're going to specify that this model must generalize arbitrarily and must scale to any number of robots n in the neighborhood of my ego robot I. And we're going to design neural network architectures that allow us to do this, that allow us to aggregate information coming in from neighborhoods so that robot I can make decisions based on this contextualized information neighborhood information. So in practice, what this means is that robot I is running a neural network that aggregates and processes incoming neighborhood information and influences what decisions it's going to be making on the fly. So now I'm coming to the actual piece of work that I want to talk about, which is this problem of modeling interaction for close proximity flight. So before I play this movie, I just want to explain to you why we're motivated to solve this close proximity flight problem. And for us, the simple reason is that currently flight is constrained by how close we can fly our quadrotors. So typically, when you launch a group of quadrotors, you have to launch them at safe distances because the airwash patterns create significant disturbances that if the robots are naive, if they don't have very specific models of what other robots around them are doing, cannot counteract, and that destabilizes them substantially during flight and hence becomes unsafe. So typically what happens today is when robots have to go through tunnels or doorways, they're doing this in a very isolated manner where groups are essentially taken over. Okay? And we want to get rid of this restriction. But in order to get rid of this restriction, we have to solve close proximity flight. And so what we do is we're specifically considering this problem of counteracting robot disturbances. And we start by saying, well, we're going to specify this problem where we have a robot that is hovering somewhere, and we're calling the hovering robot the alpha robot. And we have a second robot that we're calling our beta robot, or the suffering robot, that has to track a desired trajectory. And ideally, we want it to be able to track the desired trajectory exactly as specified, irrespective of the downwash patterns being created in its neighborhood. So it needs to be able to model these downwash patterns so that it can execute some disturbance rejection during its control. And so the dynamics model that we assume is, well, we have, we're specifying this single integrator model where we have our regular dynamics, and then we have this residual term Fx or F exterior that we're trying to estimate so that we can integrate it into our onboard disturbance rejection controller. Now, what's important to us is that we're going to be specifying a couple of key requirements. And the key requirements that we're going to be specifying is that, well, we want these model force predictions to be three-dimensional. So not just in the down direction of the hovering robot, but in the full space that the robot is consuming here. The model has to be able to run on board because we're running the onboard control. We're running the disturbance rejection controller, the robot controller. We're running it on board. So these the inference of our model predictions has to be run at a minimum of 50 hertz. And because our robots, which are designed and built in-house, are running Raspberry Pi controllers or boards, the model has to be relatively small. So these are 8 gigabytes Raspberry Pi, so the model can't be arbitrarily large. We have a couple of real-world systems constraints here that we have to satisfy. So given these constraints, we really looked at methods that would not only squeeze the model size, but also alleviate the challenge of actually learning the system with our quadrotors, given that learning or collecting real-world data with quadrotors is also very expensive in terms of not only effort, but also time and safety. So how do we simplify the learning process? And here's where the symmetries come in. So the intuition that we had was basically guided by the following. So even though airwash patterns are incredibly complex fluid dynamic patterns, we know that no matter how we're approaching the downwash zone of alpha robot within this cone here, there are some symmetries that it seems that we should be able to observe and encode into our learning process. So more specifically, the intuition here is that in the frame of the leading vehicle, or in the frame of alpha, we have an equivariance of rotations around the vertical axis of alpha's body frame. Okay? And so we're going to be encoding this as a geometric prior into our learning algorithm, which in turn will allow us to reduce the dimensionality of the problem and learn in a much more data efficient manner. So ultimately, despite of the complexity of downwash patterns, we're hoping to be able to capture them efficiently with a quite small and efficient model. So let me just formalize this a little bit for you here with this graphic here. So again, we're going to be speculating or stipulating, pardon, that we have rotational equivariance with respect to the frame of the leader robot. And our input, or the combination that is going to be subject to this equivariance, is our combination delta p, which is the relative pose, and velocity of our robot, beta, the sufferer robot. So on the left-hand side, you can see a top-down view that illustrates what you saw in the animated movie before, where intuitively you can see how in the vertical axis of the leader robot, the force that is felt by our robot B is rotationally equivariant with respect to this this transform SO2 around the fixed the fixed vertical axis in the robot alpha's leader frame. Okay. So basically, in the frame of the leader frame, in the frame of the leader vehicle alpha, rotating the relative position vector and the velocity vector of robot Bravo in the A1 and A2 axes is going to be equivalent to rotating the force vector Fx by the same angle, omega. So our problem statement is as follows. What we want to do is to estimate this external force as a function of our input x, where input x initially is simply the absolute pose of alpha and beta, our two robots, and their absolute velocities. And we basically have two assumptions that we state. Well, the first one is very simple. It's trivial. It states that we have translation invariance. So basically, we know that this external force should not depend on the positional shift in the input space. And we saw this assumption of translation invariance in various forms today throughout the workshop. So writing this down a little bit more formally, we assume that our external force F sub x is invariant with respect to the group action T star x. And this allows us to basically say that x is equivalent to simply relative pose and our absolute velocities v alpha and v beta. Okay? Now, our second assumption is the rotation equivariance. where the first thing that we do is we specify H sub A, which is our set of all matrices H that contain all rotations that fix the A3 axes, which is the down direction of alpha's body frame. And then we go on to define the action of this group on input and output spaces. So the action of H sub A on the input space is H star X, which basically says that we're executing a rotation of my relative pose and my absolute velocity of beta. And the action on my output space basically states that we're executing a rotation of the force vector W here in which is in the output space of in R3. So here we have now that our external force is equivariant with respect to the group actions on input and output spaces, completing our second assumption and completing this narrative that I've been telling you about, where we're assuming this rotational equivariance prior on the geometry of our system, modeling the downwash forces in my given application. And so what does this system produce? Well, first of all, how do we train it? So we decided to train the system in a supervised training, supervised learning setup, where we collect ground truth data, we label it, we implement a relatively small, shallow network consisting of only one nonlinearity, and we perform training on our equivariant neural network with only 5 minutes of flight data. So this is as much data that you can basically collect on one battery load of quadrotor pair, which is a really elegant proposition. And in this movie, what you can see here is actually a superposition of two experiments, both with the Alpha, the hovering drone, and Bravo, our sufferer drone that has to execute the same desired trajectory underneath Alpha. And you can see that when the robot is actually running our disturbance rejection within its controller, the deviation experience on the desired trajectory is significantly reduced. And what's nice is that we're satisfying our three desired model specifications. So we have 3D force predictions. Our model is running really quickly, so we're capable of running it inboard within our disturbance rejection controller. And it's very small. It's got less than 100 parameters, which is brilliant because it means that deploying it on our Raspberry Pi system is substantially facilitated. So what do the results, quantitative results, look like, and how does it compare to other types of models that we could use in order to estimate downwash patterns? We actually compare our implemented shallow equivariant system, so the green line here, with two benchmarks. So one where we implement a shallow network but that is non-equivariant, and one that is deep, that has a significantly larger number of parameters, but that does not exploit equivariance properties. And we can see that we outperform the shallow non-equivariant system, and that eventually we perform as well as the deep non-equivariant system. But what's really striking here is the speed at which we learn. So within 5 minutes of training data already, we have almost achieved the best possible performance that we could, given the quality of the data that we've collected. And the non-equivariant system takes 3 times as long to reach the same level of performance. And so the reason that we're able to do this is because our geometry of our model is essentially exploiting these priors to reduce our system to, we're basically encoding these through data transformations and reducing the dimensionality of our problem, and thus encoding it explicitly in the way we design our neural networks. The way we're executing a training already is enforcing strict symmetry constraints. And so with only 5 minutes of flight data, we achieve very good performance already. During deployment, we're also seeing a significant reduction of tracking errors. So in vertical tracking errors, we have a 56 reduction of error, and in the lateral tracking, we have 36 error reduction, showing that the 3D force vectors that we're estimating significantly have a significant impact on the flight performance of our systems. And what you can see on the right-hand side actually here is a vector field of what the model would predict at various points in space for both the equivariant and the non-equivariant models. And you can see how regular and how generalizable the equivariant model tends to be, given that we're imposing these symmetry constraints whereas the non-hypervariant model seems to be doing roughly the right thing, but clearly is not exploiting the fact that there are certain symmetries in the way that these robots interact with each other, and hence an opportunity seems lost here in terms of how the model is learning what these external forces should look like across space. So what can we do with these downwash models before just beyond just tracking trajectories a little bit more precisely? So what I'm showing you here is a make or break example for something that you would not otherwise be able to do if you're not able to approach robots at close proximity. So this is work led by one of my postdocs in my lab, AJ Shankar, where we're considering the docking problem. And intuitively, you might think that, well, why can't we just create longer docking cables so that interaction doesn't become a problem at close distances? But the problem with very long docking cables is that those create instabilities that are, again, very difficult to circumvent. And so downwash disturbance rejection seems to be a viable proposition here. And so without them, clearly, we are not able to achieve docking at close proximities. And here is a movie that demonstrates the successful docking with Bravo, my Cepher robot that is running the model on board, here with a fixed robot on the pole. And in the next movie segment, you'll see how Alpha is actually hovering in free flight. And here we're seeing a successful dock and also undock of the system using the downwash model. So we're really excited about the kinds of things that we're able to achieve with these kinds of very elegant and tight models. So what's next beyond pairwise symmetries? So clearly, I didn't tell you the whole story. So there are definitely a couple of limitations that are associated to training and learning these kinds of models for real world systems. One is, well, the prior that I showed you today was fully based on known or assumed symmetries in our system. And we saw through numerous talks today what happens when these symmetries don't hold perfectly, or when they're only approximate symmetries of what is actually going on in the real world. And in our particular case, the symmetries definitely only hold within certain flight regimes, of which I'd be more than happy to talk about more in detail in the Q&A or in the panel session. And also, since we're training these systems with supervised learning at the minute, the quality of the labels or the quality of the data that we present our models is going to be really, really important, because that's the data that the robots are going to be using to generalize across the whole of the space. So the quality of the data becomes really paramount here. And we invested really a lot of effort and time into the filtering and understanding of how to actually process the data correctly so that it best represents the kinds of artifacts that we're trying to capture in these real world systems. There's a lot of interesting future work that we think we should be doing in multi-agent systems in the real world. So we're looking into, and this is partially also kind of a list of teasers of some of the things that we're working on. We're looking at uncovering regularities of the aerodynamics in swarm flight beyond just two robots. We're looking at symmetric interaction patterns for robots that are engaged in formation control, which under certain scenarios can have significant symmetries in the way robots move. And we're also looking at role symmetries and so on in other types of applications represented by game theoretic scenarios. And there is also much more that we can think of. And I know that Elise talked about a few in her talk within the realm of multi-agent and multi-robot systems. So I think I'm out of time, actually. I do have a few more videos that I could show you and a little bit more that I could talk about, but I'm going to kind of like virtually stare at or look at Jake right now. Let me know if I have time to show you another movie or two. Otherwise, I can wrap it here.
Oops. Sorry, we muted to avoid echo before. You've got like 2 minutes left if you want to show a video or two, and then we'll move on.
Cool. Yeah, 2 minutes is fine. So I just want to talk about this subject of, well, what's beyond pairwise systems, because obviously I showed you this architecture before where I very boldly said that we're thinking about modeling not just pairwise interactions, but we can scale these kinds of neural networks to an arbitrary number of robots in the neighborhood. But I didn't actually show you that in the case of this downwash interaction. And so the difficulty here is really in understanding how to model aggregate downwash beyond two robots. And the key problem that we're facing here is, before we even think about considering symmetries, is, well, what kinds of models do we even have to use in order to be able to model the aggregate downwash forces that are felt by sufferer robots? Is this going to be a linear model, or do we have to assume nonlinear models? And the nice thing about linear models, obviously, would be that we can collect pairwise robot data as we did before, and this then extrapolates to k plus, n, however many systems, however many robots are part of our system. But if the interactions are only represented through nonlinear models, then we clearly have to collect data specifically for every combination of robots in the neighborhood, k, since we require a nonlinearity around the inside of the pairwise interactions that robots are feeling. And so here, what I'm showing you here is how we're going about understanding what kind of interactions are actually going on here. And one of my PhD students, Jennifer, designed a really intricate flight rig system that can measure downwash forces across all degrees of freedom here on a sufferer robot. And you can see how we're now increasing to not only one, but up to 3 robots in the vicinity of this robot collecting data, so that we can glean a little bit more information on what kinds of downwash patterns we're actually feeling here, and whether or not linear or nonlinear models are the way to go, and what kinds of symmetries we might be able to be exploiting in these systems. Our empirical results were presented in an ISER paper at the end of last year, and I invite you to have a look at those if you're more curious. So with that, I'm closing. Thank you very much for your attention. I'd like to thank my lab and my collaborators for all their hard work on systems. And with that, I'm happy to take any questions. Thank you.
Thanks so much, Amanda. I think we have time for one question before we move to the panel discussion.